Waves are oscillations of matter traveling through a medium. We know a lot of types of them, like sea waves that are right behind it. In this case, the medium is the water. We know other type of waves with other type of mediums, like sound waves, in which case the medium is the air. Until the 19th century, scientists thought light behaved like these waves, so it needed a medium. Come on, I will explain it better to you. Imagine the light traveling from the sun to the earth. According to the 19th century way of thinking, light couldn't travel in empty space. It needed a medium. This medium was called luminiferous ether, which was an invisible and infinite material with no interaction with physical objects. However, if the Earth moves relative to the ether, it will cause a sort of ether direction, which is called ether wind. So, if it exists, we can notice it because light should move faster in the direction of the ether and slower in the opposite way. So, in 1887, Albert Michelson and Edward Morley were attempting to prove if this ether was real, so they tried to detect it. For this, Michelson designed a device that emitted light through a half-silvered mirror used to split it into two beams traveling perpendicularly, until the end of the arms of the device, where the beams were reflected to the middle again, where both would be reflected to another arm that ended in a detector. If there was an ether, the expected was that it should be a delay between the two beams. But that didn't happen, and both beams arrived at the same time at the detector. This was called Michelson-Morley experiment. After they dropped out of this ether idea, the scientists faced a big problem, because they didn't know how things like light moved. So, they started to think out of the box, and discovered that things like time wasn't absolute. But first, let's give a look at frames of reference. Einstein said that the laws of physics are the same for all observers that are in uniform motion relative to one another, or in an inertial frame of reference. In these conditions, we can even play rackets. So, at the moment, I am with zero velocity relative to the car, so these conditions will be respected. But if the car suddenly stops, this law will be violated thanks to inertia. Now we are ready to understand special relativity. This awkward theory which allows time to dilate and objects to shrink has only two postulates. One says that the laws of physics are the same for everyone's perspective while in uniform motion. This is why I can play rackets in the car, no matter its velocity, the same way as if I'm standing still. And the other one says that the vacuum speed of light is the same for all observers. So, no matter your velocity, if you emit a light beam, its speed will always be 300,000 kilometers per second in every reference frame. That's crazy, right? Now let's talk about the twins paradox. Imagine you have a twin, and you are traveling at top speed of light in a rocket, while your brother is stationary on Earth. Both you and your brother have similar light clocks. These clocks work with a pulse of light bouncing between two mirrors, and every time light touches mirror 1, you count a tick. If your brother watches your clock, things start to get awkward because of your sideways motion. Your brother sees that the light in your clock needs to travel a longer path between the two mirrors, and since the speed of light is the same for all observers, she can say that your ticks pass slower, and so the time passes slower for you rather than for your brother. This isn't a nautical illusion. In fact, this really happens. Isn't that amazing? Your trip lasts 10 years, but thanks to this crazy phenomena called time dilation, when you arrive, you are almost 1 year and a half younger than your brother, because in your frame of reference only passed 8.6 years. The twins paradox is a bit more than that, but I find this a good analogy to describe special relativity in time dilation. After Einstein published his famous paper about special relativity in 1905, he started to think in how gravity would interfere with space and time, and in 1915 he published general relativity. Einstein's relativity is being a fundamental tool for the evolution of science, and it had a big role on the development of GPS and others. However, unanswered questions still remain, because the two biggest theories in physics, relativity and quantum mechanics, have a lot of incompatibilities. The biggest pretension of physicists is to create a unified theory that combines quantum and relativity. Remember that you can be the one that changes the future of physics, so don't be afraid to create your own theories, and thanks for watching.